Before we can really begin to discuss hypothesis testing and the various methodologies related to such, we should first discuss and understand central limit theorem. This is a difficult topic to lecture on as the topic itself encompasses a broad litany of subject material. I'll try to do my best, and as always, the code from today's video can be found in the video description. So we'll start by discussing central limit theorem as a definition. In probability theory, the central limit theorem states that under appropriate conditions, the distribution of a normalized version of the sample mean converges to a standard normal distribution. This holds even if the original variables themselves are not normally distributed. Now, on the topic of point estimate, which we'll also be covering in this lecture, a point estimate is a numerical summary for the sample. A point estimate is unbiased if its sampling distribution is centered at the value of the parameter, and the sample mean, x, is an unbiased estimator for the population mean. Now, what this means will become clear as we go through some of the examples that I've set up. So this is some R code here, and we're going to go ahead and work through it in RStudio. So what I've done is I've set a random seed, and from that seed, we're going to use the rnorm function. And what rnorm is going to do is it's going to create a normal distribution with a mean of 30 and a standard deviation of 10. And from that population, it's going to select at random 10 observations. So we have a normal population, mean of 30, standard deviation of 10, and we're going to select 10 samples from it, 10 observations. B is going to, vector B, we're going to have the same function, rnorm, and instead we're going to do 100 observations from the population, same mean, some standard deviation. And for vector C, mean of 30, standard deviation of 10, same as vector A and B. But in this instance, we're going to have 1,000 observation samples from our population. So let's go ahead and run each bit of code here. And you can see in the right portion of RStudio, we have our vectors being created. Now let's take a look at the mean and standard deviation from each sample. So again, these are all coming from or being drawn from the same normal distribution population. The only difference is the number of observations. So let's take a look at the mean and standard deviation for A. And A only has 10 observations. So we have a mean of 30.74, we'll round it to 30.745, and a standard deviation, we'll round each one of these to two significant figures, a standard deviation of 9.54. And here is B, and here is C. Now, what you can notice from C as compared to A and B, C has a mean of 30.20 and a standard deviation of 10.05. And those values, the mean of C, those observations, and the standard deviation of C, those observations, because there's more observations, those values are actually closer to the true mean and standard deviation of the population from which we're sampling. Now, if we wanted to plot this data, this code would achieve that for us. And what that would do is it would plot the normal distribution. Well, actually, it wouldn't be a normal distribution, but it would plot the distribution samples in each instance, A, B, and C, as they were sampled from the normal distribution. So let's go back to the slides and take a look at that. So these are the values from when I had initially created these slides. Code is still the same though. But as you can observe from the graphics on the screen in front of you, with each addition of observations, our data comes more so to resemble a normal distribution. And as you saw from the summary statistics, which we had collected as it relates to each observational series, each vector, the more observations we have, the more accurate of an estimate we have for the mean and the standard deviation as it relates to the population from which the observations were sampled. So, as we continue to collect samples, in theory, we should have a greater estimation of the population mean and a greater understanding of the underlying data. Now, how does point estimate come into play as it relates to all this? So point estimate comes into play when trying to estimate a population mean with only a singular observation. So what does this mean? I'll give you an example, and hopefully this makes point estimate clear and what the concept of point estimate is trying to demonstrate. Imagine that you have a classroom of students and you're sitting outside of the class with no way of observing the students on the other side of the door. If one student walked outside the classroom, past the door from where you're positioned, that single student, whatever their weight is, that particular student, that would be the best estimator for the mean of the weight of the entire class. So if you have a population and you only have one single sample observation from that population, your best estimate as far as guessing what the mean of the population is just in that single observation. So that one student that walked out of the class, perhaps they had to use the restroom, their weight, whatever it may be, would be the best estimate that you have available as far as it pertains to guessing what the mean is for the entire class. If you were to take the weight of every student in that class, add them together, and derive the mean. Now with two students, so let's say that one student went back to class and another student came out. If you took that student's weight and then you combine the weight with the first student whose weight you had measured, that mean would be an even better estimator. So as you continue to collect samples from the population and derive the various statistical descriptors, you can then begin to draw inference as it relates to different attributes of the actual population itself. Now let's take a look quickly at the Poisson distribution, because this phenomenon holds true for the Poisson distribution as well. Although the Poisson distribution will not come to resemble a normal distribution, just with more observations, the distribution, the Poisson distribution, will come to more so resemble the population from which the samples were drawn. So if you wanted to, you can perform some sampling in and some simulation in RStudio. And in this instance, we're going to create some Poisson distributions. Should be one right here. And we're going to sample from them. So we have the seed set. In this case, we want 10 observations from a Poisson distribution with a lambda of 12. And in each case, the lambda is going to be 12. And we're taking random samples from a Poisson distribution, assuming the lambda is 12. In this case, it's 10 observations from the underlying population, 100, and 1000. So let's do that here. There's A, B, and C. And as you can see, in this instance, it did not hold true. But as you can see, with the more observations you have, typically you're going to have a greater and more accurate understanding and estimate for the population distribution from which the observations were selected. And if you wanted to create plots as it relates to these samples, this code will achieve that for you here. So let's return now to the slides. And here's a look at it in our studio from the prior instance in which I performed these exercises. 10 observations, 100 observations, and 1,000 observations. And interestingly, you can see, again, that this is coming to resemble the appropriate distribution as it relates to the population and the lambda. So that is it for this particular lecture. I hope that I was able to make this topic clear to you for whatever your uses may be. It's interesting when we talk about central limit theorem because there's so much more that we could discuss, even though this was just a general introduction. We could talk about crowd predictive models versus single expert models and how they contend. We could talk about crowd intelligence, and perhaps that'll be a topic which I'll cover later on because it's more intermediate than what we've covered in today's lecture. But if you were able to take anything away from this, if it was able to assist you with your knowledge as it relates to this topic, please consider liking and subscribing, and I wish you all the best. Have a great rest of the day. Take care.